For engineering design, we are going to consider two extreme cases, and of course, the whole transition is important, but let's get the asymptotes right. The first asymptote is making sure that the settlement is going to be acceptable. And so, let's remember what settlement is about. Is the integral of the vertical strains, let's say that we are looking at the foundation, but it can be for any geometry, is the integral of the vertical strains in depth. And we are not going to go to infinite, probably we are going to go to 2 to 4 times the characteristic length scale of our foundations, but conceptually this is correct. Now, if we take the quasi-linear elastic asymptote, we can rewrite this equation as the integral from 0 to infinite of 1 over E sigma z minus Poisson sigma x plus sigma y. And we wrote this equation in this general form, but as we said in that corresponding video, please realize that these are changes in stresses, because the change in stresses that are causing the granular skeleton to change and to give rise to strain, and in particular, we would like to do changes in effective stress. On the other hand, when we check whether a system goes to failure, remember that we are going to check failure, let's say, in a tau sigma or QP space, where this is the failure envelope. So our initial state of stress was here, where this was the initial sigma 1, the initial sigma 3, and then we changed the state of stress to eventually reach failure, and this is the ultimate sigma 3, and this is the ultimate sigma 1, such that the sigma 1 over sigma 3 ultimate reaches the maximum stress anisotropy in terms of effective stress, which in this case would be tangent square of 45 plus phi over 2. So this is the limiting stress anisotropy that a granular material may sustain. Notice that this was our initial state of stress, sigma 3 initial and sigma 1 initial effective. Then we added delta sigma 3, we added delta sigma 1, but we are checking failure by the combined state of stress, the sigma 1 and the sigma 3 ultimate, not by the increments which cause settlement, but by the combined stress between the in situ and the added ones. Now, in all these cases, we have that sigma effective is equal to sigma minus u. And now the question is, what u do we use? And we have seen several mechanisms that cause pressure in the fluids within the sediment. And so let's go back and recognize all these processes, these causal systems, and understand what are the implications. So let's review the basic cases. The first one is a hydrostatic. The system is like in a swimming pool, and we're going to put the water table beneath the surface. And in every case, for saturated materials, if you ever have any doubts, put in your mind a piezometer at the location of interest and look how high the water rises in the piezometer. So this piezometric height times the unit weight of water is going to give you the pore pressure, always. And in this case, because of communicating vessels, the fluid will rise in the piezometer all the way to the water table under hydrostatic conditions. The second case is the case of seepage, and let's go back to analyze a simple flow net configuration. And so we have to satisfy normality, which I'm not doing it, but for the sake of a sketch, if I place anywhere a piezometer, I will be able to determine how high the water will go. And the water in this case will not go as high as the hydrostatic condition, because this is not hydrostatic, this is a steady state seepage. So we have to go back and check what is the total head at the entry, at the exit, how many equipotentials, how much energy I have lost, and probably the water will rise to this elevation. So this is the piezometric head. And so once again, U is equal to piezometric head times the unit weight of water. Once again, it will not go up to the hydrostatic condition because this is steady state seepage. Now, for load induced, the story gets more interesting because this could be isotropic loading, K0 loading, that means zero lateral strain, and deviatoric loading. And we have to wonder what are the pore pressures that we generate in each case. So for isotropic loading, imagine that we have soil packing inside the balloon, and we seal it, it's saturated with water, and we apply confinement. And if the water is really very stiff, so the bulk stiffness of water is very high because the soil is perfectly liquid saturated, and so the bulk stiffness is much greater than the bulk stiffness of the skeleton, and the minerals is going to be here, be mineral greater than the bulk stiffness of water. In this case, the change in pore pressure is going to be equal to the change in confining stress. So this is delta sigma confinement, and whatever you do, it will be felt by the skeleton. And this is called, if this is not truly 1, we need to multiply times a parameter which we're going to call B, is called Skempton's B parameter. But once again, when soils are low effective stress and 100% saturation, then the Skempton's B parameter is equal to 1.0. If this is approaching a rock, now the skeleton has such a high stiffness that you cannot make this assumption, and there will be a little bit of compressibility of the water, a little bit of compressibility of the skeleton, and now the pore pressure generation and the skeletal participation will have to come together to compensate for the confining stress, and so it will be slightly or significantly less than 1, let's say in a sandstone. For zero lateral strain, this goes to the case of the odometer, and if the soil is perfectly saturated and we apply a delta Q, and we measure with an internal pore pressure transducer the delta U, we're going to see that delta U is equal to a fraction or a percentage proportional to delta Q. Once again, if the condition above applies, in other words, the mineral is very stiff, but the water is much stiffer than the skeleton, then this parameter, which we call C, for 100% saturation and no cementation, the C parameter is also approximately equal to 1.0. Now the question is, what happens when we do deviatoric loading? When we do deviatoric loading, now we have to go back to remembering what happens in a QP space. And as you may recall, if we were in a QP, which is a tau sigma effective, or we could put here QP, and we initially apply effective stress, isotropic effective stress, and then we loaded with deviatoric loading in axial compression, let's say this was the path that we were trying to follow. But if the soil built up pore pressure, now you may remember that Q is not sensitive to the pore pressure because it's the difference, and the two sigma 1 and sigma 3 experience the same pore pressure, so the pore pressure doesn't affect Q, but P prime is affected by the pore pressure both in sigma 1 and sigma 3, so P prime shifts with the pore pressure. And if the pore pressure is positive, the actual stress path moves to the left. If the pore pressure is negative, because the soil is dilative, the actual stress path moves to the right of what you are imposing. The pore pressure is related to the applied deviatoric load, but that parameter will tell you whether it goes to the left or to the right, and so now the pore pressure is going to be a function of the sigma deviatoric times a parameter that we call A. And that A now can change quite a lot, because imagine that this was 45-degree angle, and if you create as much pore pressure as the deviatoric load, that means that you're following a vertical path. So if you're following a vertical path, the A parameter is 1. Now, if you are moving towards the right of the imposed stresses, that means that you're building up negative pore pressure, and the A parameter will be less than 1. Furthermore, notice that the path curves. That means that the A parameter changes along the path. So this is not really a very easy to define parameter, and it's all established by the actual stress path that the material wants to follow. The A, B, and C parameters are called Skempton's parameters. You may have heard that we use the Skempton's B parameter to assess whether the soil is saturated. When you are going to run a liquefaction test, the first thing that you do is you change the confinement and close the valve, change the confinement to see if you generate a pore pressure equal to the changing confinement. Then you have a B parameter 1, you have a perfectly saturated soil. Folks, please recognize that because we are running out of characters, we are calling the bulk stiffness with the letter B, and it turns out to be that we also call Skempton's B parameter for isotropic loading B. But these B are stiffnesses, and these are the Skempton's A, B, C parameters, while these are bulk stiffnesses. In the case of a triaxial test, you may have applied some confinement, close the valve for drainage, for the specimen drainage, apply more confinement, and then apply the deviatoric load. And so now you may wonder how much pore pressure you have generated on the two stages, when you apply the additional confinement and when you apply the deviatoric load, and you may add them up as shown here. Sometimes, because the A parameter will be affected by the degree of saturation, you may see that this equation could be in parentheses where B is a factor of both of them or not. To summarize, before I erase this board, the pore pressure, the pressure in the fluid that is within the pores, could emerge because of hydrostatic conditions from a steady state seepage or induced by the load that we are applying, whether it is isotropic loading, zero lateral strain, like a very large footing on a flat surface, or by deviatoric loading. And if we really want to do an effective stress analysis, we have to be able to anticipate the pore pressure in each case. I'm coming back to generalize the load-induced pore pressure generation. Every time we plot tau sigma or QP in the standard way that is done in the US, coming from Moore circle, as you realize, we are paying attention to sigma 1 and sigma 3 because these are the extreme conditions that give me the maximum stress anisotropy to know whether I am at the failure envelope or not, whether the soil has failed or not. One of the first criteria that we had on the first board, settlement and failure. However, actually there is an intermediate stress, which is sigma 2, which is also changing. And so we actually have the three more circles defined by sigma 1, sigma 2, and sigma 3. And actually, we should not totally disregard sigma 2. It does affect the behavior of the soil. And so if we want to represent this in the proper condition, we should be looking at the 3D state of stress. So this is sigma 1, sigma 2, and this is sigma 3. And this will be the isotropic axis, whereby sigma 1, sigma 2, and sigma 3 are the same. So a given state of stress, for example, a point somewhere here, could be reached by going along the isotropic axis and then cutting across, where this is going to be the octahedral stress, and this is the octahedral shear stress. And this is a better representation because I have the 3D state of stress, the octahedral stress being the average of the three, and the octahedral shear stress, the Pythagorean length of the 3 deviatoric components. In this case, the induced state of stress can be generalized by saying there is a B parameter of delta sigma octahedral plus an A parameter of tau octahedral. And instead of using the previous Skempton's coefficients, these A and B are called the Henkel coefficients. Once again, you can derive them theoretically, and you will see references at the end of this video for these parameters, but actually they are, particularly the A parameter, is changing throughout the loading history, so it becomes not that obvious parameter to anticipate to come up with a whole path, except that you may have values for the failure conditions. Fluid pressure in a system that is unsaturated, and we call that the suction. We suggested that it could be done through a Bishop's conditions if things work well. Otherwise, the parameters have to be explored in terms of two independent state parameters, being the ones created at the boundary stress minus the U gas at the boundary, and the U gas minus the U water, which is the suction, and these two are going to control the behavior. So whether you bring them together in a Bishop formulation for a large number of simple cases, or you actually keep them separate, will affect how you do the analysis. There is one more situation which is caused by chemical processes. For example, if I had a clay and all of a sudden I subject it to a high concentration front, then the first thing that will occur, because this high concentration with respect to the clays will act as a semi-permeable membrane. So the first thing that will happen is that water will go from right to left to lower the concentration on the left. And this is going to cause an osmotic suction. Thereafter, eventually, these ions are going to invade by diffusion, increase the ionic concentration, shrink the double layer, reduce the repulsion minus attraction balance between forces, what we call the DLVO theory, and this is going to cause contraction. And in the process, depending on the rate of diffusion and the rate of pore pressure dissipation, there could be an excess pore pressure, the sediment is contracting and the water needs time to escape, or not. It could all just lead to overall contraction. So this is a chemomechanical coupling. Now, all these processes that are caused by the application of a load, the evolution of suction, and the evolution of chemical processes may be time dependent and are going to create transients. So I'm coming back to make a brief comment about the analysis for transient conditions. We have seen in the previous slides that the application of loads, changes in boundary conditions, cause changes in pore fluid pressure. Now, eventually, there will be drainage, and eventually those excess pore pressures will dissipate and go back to the steady state seepage or steady state hydrostatic conditions. And so, how do we analyze this case? Let's make some sketches. So this is the initial condition before the application of a load under zero lateral strain boundary conditions, K0 conditions, and the hydrostatic pore pressure increases. If it is hydrostatic here, it will increase linearly with depth. There is no artesian, so it's all a swimming pool type condition. Now, as soon as we apply the load at time t0, this initial condition, if it was perfectly saturated and the Skempton C parameter is equal to 1, all the pore pressure will increase, and this change in pore pressure is equal to delta Q, the applied load, because we're assuming that saturation is equal to 100%, and therefore we are lack of cementation in the sediment, so therefore we are saying that the Skempton C parameter is equal to 1.0. Therefore, that is the excess pore pressure that is generated. So this delta U, or we can call it U excess. Now, by the time we come here, all the excess pore pressure at time infinite has dissipated, and we go back to the hydrostatic condition. And now we have two ways of running this, for example, in the finite difference formulation that we did in one of the previous videos. I could just look at the excess pore pressure and see how it dissipates. And in that case, if I just look at the excess pore pressure, I will have a diagram as follows. This is U excess. At the beginning is equal to delta Q, and so is a rectangle. And as time passes by, let's say that is double drainage, it will begin going down, and you can compute that very easily numerically in Excel, following the previous video, or there are closed form solutions. And you see it looks as half a sinusoid, so it gives you an idea of what will be the shape of the solution, of the closed form solution. And so at any point, you can see what is the U excess at every instant in time. This is as time passes by. And you can see at any point, at any depth, and at any time, what is the excess pore pressure that you will add to the hydrostatic pore pressure to determine your actual pore pressure. So if you follow this path, that you are dissipating just the excess pore pressure, then the pore pressure is equal to U static, hydrostatic, plus the U excess as a function of Z and time. Of course, this is also a function of Z. Now, the other possibility that you can do, if you use the finite difference formulation, is actually to say that your condition is combined pore pressure, the excess plus the in situ, and so you're going to start with, this is your initial condition, and you're going to say that this is my final condition. And so beyond the boundaries, you're going to have a drainage condition, and you're going to come here, and this is your initial condition with drainage. So as you can see, immediately after the first time step, your boundary is going to go to 0, and then this is going to continue evolving, and at any point, you will be able to come here, and you will see what is your pore pressure, but this is your combined pore pressure. This already includes the U hydrostatic plus the U excess, and it's going to come out directly from your numerical simulation. So your end boundary condition will determine the convergence of the simulation, and in that case, the two of them are already taken care of, or just the excess, and you will have to add the hydrostatic to know the final combined pore pressure. Now, in most cases, people will just look at the excess because the diffusing excess is being transferred to the effective stress, and that is the one that is going to cause the changes in effective stress and the strains, for example, for settlement computation. Either way is totally the same. Make sure that you recognize your boundary conditions for the simulation so you don't fall into misconceived analysis.